Good afternoon or good morning if you're based in South America, like our speaker today. My name is Matthias Sterlich, and I'm hosting the Heritage Science webinar series by the E-RIHS European project and by the European Research Infrastructure for Heritage Science. This is the second webinar in 2022. And of course, this is our second year of running the webinar series, featuring the latest and most exciting research in heritage science, as well as topics otherwise related to heritage science and heritage science infrastructures. We have a particular pleasure today of welcoming a speaker from Brazil, who will be talking about new synchrotron light sources in paleontological studies. His name is Dr. Douglas Galante, and he's a researcher and group leader at the new fourth generation Brazilian synchrotron, the Sirius. Douglas's group is associated to Antecipa, the Brazilian National Association for Research in Technology and Heritage Science, which is itself an E-RIHS partner. They have been studying the paleontological record at the nanoscale, using a variety of analytical techniques in an approach called nanopaleometry. From the astrobiological perspective, it is their intention to understand the oldest fossil records on the planet so that they can be used as models of what to search on Mars for evidence of past life, for example. Douglas has a background in planetary sciences and currently works in the field of astrobiology, investigating techniques that can be used to detect faint signals of past life in the geological record. For that, he has been using the terrestrial paleontological record from deep time as a proxy. Sounds like a really exciting topic today. And I'm really happy to hand over the screen to you, Douglas. Over to you, please.
Thank you very much, Mattia, for the very nice introduction. So let me share my screen here. Okay. So thank you for this very kind invitation to present our ongoing work. It's much more than a finished work, but we are still in the beginning of this huge road, which is the nanopaleometry. We are learning how to use it to uncover more about the life on our planet and eventually on other planets as well. I'm currently based at the Brazilian Synchrotron Light Laboratory called LNLS, which is part of CNPEM, the National Center for Research in Energy and Materials, which is a federal laboratory based in Brazil, very close to São Paulo, on the city of Campinas. We are about 100 kilometers from São Paulo. And today I'm going to talk a bit about synchrotron. If you don't know what a synchrotron is, what it can be used for, and I'll show some applications in paleontology so that you can you know what can be done. So let's get started. So synchrotrons are essentially very big X-ray sources. So they produce X-ray light. And as you know from the Oettinger's experiments on the 19th century, X-ray light or X-ray radiation has the property of going through matter almost unstopped. So it can transverse matter with minor diminishing of intensity. And this was showed by Oettinger when he used it to produce the first radiography on the history, which is his wife's wedding ring. We can see the wedding ring here and in his wife's hand. And so very soon after this discovery, X-rays were, of course, applied on medicine, and they made a huge revolution on the world wars. So they allowed to have a diagnostic method, a non-invasive diagnostic method almost without any cost, any harm for the patient. Of course, there would be harms later with radiation that would be later discovered, but this is a different issue. But it's very important when we talk about cultural heritage materials as well, because they can be damaged by radiation. And this is an issue that we can discuss. So if you want to ask about it, go ahead. I'd like to discuss this matter. Well, there are a variety of sources of X-rays. The most common ones are cathode ray tubes. So essentially, it's a very small electron accelerator, which excites a metal plate, and this metal plate will give off fluorescence X-rays. And this can be used for a variety of techniques. So these are used on common X-ray tubes for the medical industry, for the diagnostics, treatment, whatever. At synchrotrons, we have a different way of producing X-rays. Essentially, what we do, we use electrons as well, but we trap electrons using an intense magnetic field. And when the electrons circulate around this magnetic field, suffering the forces of this magnetic field, they will give off radiation. This is a property of nature. Every time you have a charged particle being accelerated, such as to turn its direction, it will give off X-ray, it will give off electromagnetic radiation. And if you are at the right energy of the electrons and the right intensity of the magnetic field, this will give off mainly X-rays. So we tune our machines to produce X-rays, and they have to be very big. This is Sirius, the Brazilian synchrotron light source, seen from above, and you can see that it's a very big machine. So we depart from a system which has about 10 or 15 or 20 centimeters, and we go to machines which have about 1 kilometer in length. So the machines are much bigger, and the intensity is much higher than the common X-rays. I'm going to talk more about the advantages of synchrotron radiation soon. So a synchrotron accelerator, as you have seen, is normally a round accelerator. So we have around what we call a storage ring, which is essentially a pipe kept in vacuum, where the electrons circulate throughout the day. So the electrons are produced, they are accelerated, they are inserted on the storage ring, and they are maintained circulating around throughout the day. And from time to time, they will pass through special electromagnets, which can be of different types. They can be dipoles or multipoles. So they can be dipoles or what we call ondulators. And when the electrons go through these special devices, essentially, the electrons are going to wiggle around. They're going to make very small turns inside the magnet, and then they go out and keep their common revolution. Every time that the electron makes a small turn inside the magnet, it will produce a bit of radiation. Then it will turn to the other side, a bit more radiation. Turn to the other side, a bit more radiation. And this radiation will sum up and will come out and be inserted in what we call a beamline, which is essentially an optical system composed of monochromators, focusing optics, which can be, and normally are mirrors, metallic mirrors, or zone plates, or different types of focusing optics of different types. And here the light that comes out is conditioned for the experiment. So it's monochromatized, we select the energy to work, and it is focused or collimated to the specific size that we need to perform the experiment in question. And then it reaches the sample, and a variety of physical phenomena happen in the sample. Essentially, we can have X-ray absorption, and we can get the profile of the X-ray absorption, which can give us the oxidation state, the local coordination, and the bond distances of the sample of the samples being studied. It will give off fluorescence photons that can be analyzed in a special detector such as an EDX detector or a crystal analyzer or different types of detectors. And we can have the chemical composition at very small scale with very high sensitivity, much higher than a common EDS, electron microscopy based EDS. Electron microscope based EDS, you have a sensitivity on the percent scale. Here we can go down to ppm or even ppbs in terms of sensitivity. And we can do elemental mapping as well. We can get diffraction patterns if the sample is crystalline, so we can get a sense of the ordering and the mid and long range structure of the material, and we can get the stress, strain, and texture mappings of the samples as well. And more recently, with the 4th generation machines, we can explore the coherence of the beam. Essentially, the beam that is being produced by the machine is almost like an X-ray laser. All the photons are on the same phase. And so that's what we call a coherent beam. And when photons of the same phase transverse a material which is mildly organized, it will be scattered in a very specific way. And with this, we can analyze the coherent diffraction, the coherent scattering, to produce very high resolution images of the materials. And I'm going to show us an example of this at the very end of my talk. So we can have a lot of different physical phenomena out from the very same photons. And in synchrotrons, depending on the beamline, we can have beamlines that are specialized in one type of measurements in diffraction or in absorption or in fluorescence. But in some beamlines, we can collect all these and almost at the same time. And that's something that's very useful when we want to really understand the nature of the sample that is being studied. This is a comparison of the X-ray emission from an X-ray tube, a copper X-ray tube, which is essentially monochromatic. So it's monochromatic with a background, but it's essentially monochromatic. With 2nd generation machines, which are now retired, such as the oldest Brazilian one, which is now retired. But we can see here some advantages. Synchrotron machines have a very broad energy range that goes from infrared to hard X-rays. So we can probe different types of phenomena, of physical phenomena, with this very long range. We can do molecular spectroscopy and we can do core shell electron spectroscopy with the same machine. So that's something that's amazing. And the intensity is much higher as well. We can see here it's in log scale. So it's several orders of magnitude more intense than a common X-ray tube, which allows to do much faster experiments and to get much more sensitivity. Well, currently most of the machines are 3rd generation ones, which are over here, and we can see there is a gain of several orders of magnitude in terms of intensity to the 3rd generation machines. And nowadays we are coming to the 4th generation machines, which have much higher intensity that would be up high here. So with this, with synchrotron machines, we have a very high flux, a broad energy range, the possibility to tune the energy, to select the energy, to monochromatize the energy, the possibility of collimating or focusing the beam at very small scales, nowadays at nanoscales. The world record is a few nanometers, and to explore the coherence of the beam, such as an X-ray laser. This gives us very high spectral resolution, very high spatial resolution, the possibility to do, and the possibility of applying multiple analytical techniques for the study of your specific materials. Of course, there are some drawbacks. It's very, the techniques are not plug and play. Normally they demand training. So a new user takes a few years to become an experienced user. The techniques are expensive. The beam time is expensive. Normally, synchrotron accelerators are maintained by the government, and and the proposers are selected in a competitive manner. And the competition is very high because it's very expensive. That comes out to this. Of course, it's not portable. You can't take this to Mars or to a museum. You have to take your samples to the synchrotron facility. And sometimes you have to prepare the synchrotron facility to receive a work of art, a painting or something like that. And it's meant for more specific and complex problems than common measurements that can be done with benchtop equipment. Well, this is our old synchrotron. Maybe a few of you on the audience have met this. This is the E-RIHS machine, which operated from 1997 to 2019. So many, many years of continuous operation. It was the first synchrotron on the Southern Hemisphere. Australia opened its one in 2005 only. So we have been the first ones on the Southern Hemisphere. We are about 30 internal researchers, such as myself. We receive about 1,500 external users per year to use our facility. So we are maintained by the federal government to be an open user facility for the whole country and abroad. We are open for international users, in fact. Of course, we host a lot of postdocs, students from all levels, engineers and staff to keep it working. And the mission of the facility is to be an open facility for the Brazilian and the international communities. All the measurements performed at the Brazilian synchrotron are cost-free for academic users. So this is paid by the government, by the federal government. But for the industry, we charge there's some costs involved, of course. So this is our campus. This is the CNPEN campus. This is the old LNLS. So this was the old synchrotron, and I'm going to show the new one very soon. We operated in synergy with three other national labs: the Nanotechnology Lab, LN Nano, the Biosciences Lab, LN Bio, and the Biorenewables Lab, LNBR. All are focused in specific and important problems for the Brazilian and the international communities, such as tropical diseases, nowadays COVID vaccines, bioplastics, and many other different types of issues, better sensors, whatever. But we work in synergy to solve these problems, and all of these have open user facilities to receive external users. This is the E-RIHS machine. So we ended the operation with 18 beam lines working from the infrared to X-rays, doing spectroscopy, scattering, diffraction, and imaging on different types of energy ranges. And I'm just going to show some examples of these measurements here. So in terms of diffraction, so of course you probably know what diffraction is, but essentially what we do is we take a monochromatic X-ray beam, which has the wavelength of the same order of the spacing of the atoms on your sample, and we shine it on a crystalline sample, and it does that, it will produce a diffraction pattern. So the light will be scattered in a very specific way, giving off the information about the distances of the atoms inside your sample. When we collect this diffraction pattern, we can then do mathematics to go back to the real space, to the actual distribution of atoms on your sample. And this is an example, a very classic example of diffraction. You probably know this picture because it is the picture taken by Watson and Crick. Now we know it was stolen from Rosalind Franklin, of course, but it was used to uncover the 3D structure of the DNA, the double helix structure of the DNA. So this is the power that we can take out from these simple diffraction images. We can uncover the structure of molecules and different types of materials, of crystals, of minerals, of all sorts. And essentially, if you take any textbook, when you have a macromolecule, a protein or a lipid, which is, and you have this structure, you can say that it was most probably produced on a synchrotron machine. Of course, Watson-Crick didn't have a synchrotron machine back then. They did it with a conventional X-ray tube, but nowadays we do it synchrotrons. But in synchrotron machines, we can do better because we can focus the light. So we can take information from very small patches of your sample. This is an example of micro diffraction taken from a meteorite. So we can analyze the phases of the materials directly. So we can really shine the light in a specific phase of the meteorite, collect the diffraction pattern, and say, okay, this is this mineral or that mineral, and you can even make maps out of it. In addition, and something that's very important for catalysis, for instance, is that you can do in situ and in operando measurements. As you have a very high flux, you can take diffraction patterns very fast, in microseconds in some cases. And with this, you can do dynamic measurements. This is an example. Here we are lowering the temperature on this X, and we can see that this peak, which represents a specific crystalline phase, is appearing, is growing up. So it's a crystallization process that can be studied dynamically with synchrotron. And of course, we can change the temperature, we can change the pressure, we can change the chemical environment and do reactions. So we can do catalysis, we can study the degradation of works of art and things like that in situ and in real time with synchrotron machines. In terms of imaging, I'm showing here some examples of tomography. So what we do in tomography is very similar to what is done at conventional medical tomography, where you have the patient, we have an X-ray tube on the top, we have a detector on the bottom, and we rotate the tube and the detector around the patient, taking radiographies. And when you have the full set of radiographies throughout the 360 degrees, you can join all these radiographies with a mathematical transformation called Hadron transformation, and this will produce the 3D image of the sample. Of course, in synchrotrons, we are not turning the synchrotron around; we are turning the sample. So we put the sample in front of the beam, and we turn it around, taking radiographies at very high spatial resolution. And with this, we can produce very high resolution tomographies. This is an example of, I think the resolution here, is the voxel size, the 3D pixel size here is about 170 nanometers. So this was the world record back then. And you can see that with this is a bone structure. And we can see inside the bone, the channels, the trabecules, and all this structure inside the bone. So this can be uncovered in 3D by synchrotrons. The resolution of a synchrotron tomographer is about 1,000 to 1,000,000 times better than a conventional medical tomography. And of course, we can see with synchrotrons the invisible. We can do elemental mapping to uncover the structures of materials from the very past. This is an example of synchrotron focalization, a measurement with a microbeam of samples. And with this measurement, what we do, we collect a fluorescence spectrum, and then we do the analysis point by point. So it's a scanning technique. We shine the light in a point, we take the spectrum, we analyze it, then we move it, analyze it again, move it, analyze it again, move it, and analyze it again. Of course, we do it automatically, computer-based, and with these we produce maps. And these maps can show very interesting structures. And these are some structures from the Brazilian Conservato Lagerstätte on the Araripe Formation on Ceará, on the north of Brazil, which is a place of exceptional preservation of fossils. And we have been studying these fossils for a long time. And here are some fossils that were essentially invisible at naked eye, and we can see them in fake colors, in false colors, represent the different metals that are chelated by the organic matter on the fossils. So in red, we have calcium, in green, we have iron, in light blue, we have zinc, in dark blue, we have copper. And here we have a composition of them all. Here we have an insect. Here we have the transversal slice of a fish. We can see the fins over here. Here we have seeds and seeds. And we have been studying these fossils, seeing the invisible, seeing structures that cannot be seen, and using them to characterize in detail the morphology, the taxonomy of these different types of living beings from the Arabic Formation. Arabic Formation is from the Cretaceous, so it goes down to 110 million years old, 130 million years old, something like that. But we can do more with synchrotrons because we can select the energy to excite the material. So we can vary the energy that we use to excite the materials. And with these, we can collect the information energy dependent, which produces spectra. So this is an X-ray absorption spectra on the phosphorus edge of samples from the Corumbá Formation, which is close to Bolivia here in Brazil. And these are some of the oldest animals on the planet. They are from the Ediacara, and they have 442 million years old. We could, with this technique, characterize the phosphorus on the sample because we wanted to show that these very early animals had hard parts for the first time. So they have carapaces, and it was very important that we show that they had phosphorus and on the form of phosphorus of calcium phosphate. And we could show not only that, but we could do calibration, specific calibrations to measure the amounts, the specific amounts of calcium phosphate that we had on the sample. So it's a very powerful technique to characterize the materials and to quantify the materials on the samples. And of course, I'm showing this for phosphorus, but we could do this for sulfur, for calcium, for zinc, for iron, for any other element that we can reach with the energy of the synchrotron. Another example from paleontological studies on the Arabic Formation. This is a work from my past student, Lara Maldanis, who is currently in Grenoble at the moment, doing a postdoc. She studied this fossil fish from the Arabic Formation. It has 110 million years old. So this guy here was swimming by with the dinosaurs here in Brazil. And we wanted to study the interior of the fossil without having to crack it open, without having to cutting it open. For this, we used tomography, very high energy tomography, because it's a big fish. It has about 15 centimeters in length. So we needed a high energy to do the tomography here. But we could see a very specific detail inside of it because of the high resolution that I'm going to show better on a movie on the next slide. But we could see the heart of the fish. And this is, in fact, the oldest heart ever found. And we could map it elementally. We could do spectroscopy, and we could show that it had preserved some key elements from its functioning while it was alive. And we applied a variety of techniques to understand better this fossil fish, of course, not only micro-CT, but micro-XRF, micro-XANES, F-tier, and many others. And this is the tomography that was produced. So here is the result of the tomography and the post-treatment, which we call segmentation, where we can evidence the heart, which is present here, and which is the oldest heart that had present even the valves inside of it. But we can see the bones, the gills, the digestive tract, and all the other parts of the fish as well that could be studied. This was published in E-RIHS in 2016. But synchrotron machines are not only X-rays. As I said, we produce light from the infrared to the hard X-rays. This is an example of the infrared beamline that we had at our past synchrotron. Here we are of lead formate on the top of silicon coupons. So we wanted to see the formation of this lead formate because it's a byproduct of the degradation of lead, which was being studied by our cultural heritage people here in Brazil, essentially Professor Tiago Puglieri and Professor Dalva Faria. And they could show with the nano FTIR that the formation of these islands, which are very small, you can see here that they have a few hundreds of nanometers across, and we could map it molecularly. So this is what we can do with nano FTIR. We can break down the optical barrier of X-rays that would limit the resolution in about 10 microns in conventional systems. And here we can have resolutions of 20 nanometers, and we can get the spectra of these regions of 20 nanometers, which is very impressive. Okay, so let's go down to Sirius and to what we have been doing nowadays. So Sirius is the new Brazilian synchrotron light laboratory, and I promised to show it in comparison to the old one. So this is our campus, this is the old machine, this is the new machine. So it's about 5 times bigger than the old machine. It has higher energy. We work at 3 GeV electron energy. The emittance of the machine is very, very small. In fact, it's one of the lowest emittances on the world, is 0.25 nanometer rad. And this means that essentially the beam can be focused to very small regions, reaching nanometric scales. It will allow us to reach hundreds of keVs, allowing us to study very big samples and very hard samples. It has about 520 meters of circumference. It has a space for 39 beam lines. Of course, not all are going to be occupied on the initial phase because they are very expensive to be built. Each beam line costs about $15 million, more or less. So it's very expensive. So we have to build them as time goes by. The whole cost of it was previewed to be 1.3 billion reais, which would be at the time that this was predicted about $500 million US. Of course, this has been scaling up because the prices are going up, blah, blah, blah. And it's a fantastic new opportunity for young researchers and challenging new fields, such as paleometry, archaeometry, cultural heritage studies. And we hope to bring these new studies for our machine. In 2013, the Sirius project was already being faced side by side with the other synchrotrons in the world. Nowadays, we have MAX4 and ESRF EBS operating as 4th generation machines as well. So we have 3 4th generation machines working at the moment, and we are side by side competing to be one of the best machines. It is very good because of its project. This is the electromagnetic lattice project of Sirius. It's what bends the electrons. So to bend the electrons, we have 5 dipoles that work in tandem and several multipoles, quadrupoles and sextupoles to make sure that the electrons that are being bent, they are being bent all together. They are not going to scatter and spread apart. And this is very important to keep the emittance very low because the beam is very small. The X-ray, the electron beam has about 7 micrometers in size. This is the size of the electron beam. And this is a totally Brazilian project. And in fact, all these electromagnets are being built by a Brazilian company called WEG. So it's a whole Brazilian enterprise. And we are very proud to say about that. We didn't just bought a new machine, we are building from scratch. The building itself is very impressive. The floor has to be extremely stable. In fact, it's so stable because we need to have beams of about 10 nanometers in a machine that has almost 1 kilometer in length. So it's very difficult to maintain this stability. And for that, we have stakes, we have 4 meters of concrete soil, we have 9 centimeters of a huge continuous slab of concrete all throughout the storage ring, all this to maintain the rigidity of the machine and to keep it stable at this nanometer scale. It's very aerodynamic. Here in Campinas, we have very strong winds, so we had to take this in mind. So the ceiling itself is aerodynamic, and the whole building is isolated from the accelerator, not to produce any type of vibration on the systems. The electromagnetic sources which are the dipoles and the multipoles, the ondulators, are also Brazilian projects. They are being built here in Brazil at this moment, and they are being built to beat the current machines. So this is a comparison of the Sirius dipole emission with Diamond on the UK and Soleil in France, and we can see that the intensity and the range of energy that it can be achieved is higher. And in terms of ondulators, it's the same. So we can get more flux out of the same electrons. And we can get coherent flux. We can see here from about 2 to 23 keV, we have almost fully coherent flux. So all the photons that come out from the machine are in phase, and it's essentially an X-ray laser that can be used to perform coherent diffraction imaging techniques. And with these new machines, we can explore more in terms of chemistry. With old machines, we could explore just these elements that are marked in green. With these new machines, we can explore essentially all the elements on the periodic table. Well, coming down to my beamline, I coordinate the Carnaúba beamline, which is the coherent nanoprobe beamline, which is essentially a spectral nanoscope that has a variety of analytical techniques attached. It's the longest beamline of Sirius. It has about 143 meters in length, so it's very big. It even comes out of the building itself. It's part of the first phase of the beamline, so it's one of the first beamlines to come online. We are operational since last year, and we have been doing scientific commissioning at the moment. And then many other beamlines are projected to be open this year and next year on the next phases. So we are populating the X-ray accelerator with the coming years. As I said, this is a spectroscopy beamline, so we can do spectroscopy on the K edge of these elements marked in red, in L edge, the ones marked in blue, and in M edge, the ones marked in green. So essentially, we can do spectroscopy of all elements on the periodic table, but most efficiently the ones marked in red. So this is the best performance of the beamline. It is meant to do imaging in 2D and 3D, and to do it in scanning mode, coupling the measurement with multiple analytical techniques that I'm going to talk more about. And one of the main techniques that is going to be developed at this beamline is the imaging by coherent diffraction, which we call Bragg CDI and tachography, which can produce very high resolution machines. So the beamline works from 2 to 15 keV, which we call this energy range, we call the tender X-ray regime. And it has 2 experimental stations, Tarumã, which works on the submicron scales, and Sapoti, which really goes out to the nanometer scales. All the optics, the mirrors, the monochromators, this is all achromatic optics, which means that we can tune the energy anywhere we want between 2 and 15 keV. We can do 2D mapping, 3D tomography, Tycho CDI, Bragg CDI, and with different contrasts. We can do fluorescence, absorption, scattering, diffraction, and optical luminescence as well, with a variety of detectors to do all this. We had first been more than a year ago, so we have been doing scientific commissioning so far. In terms of the science program, we essentially use this nanoprobe to do absorption and transmission measurements, which are X-ray absorption spectroscopy, X-ray fluorescence, and X-ray excited optical luminescence. we do scattering and diffraction, essentially tychography, Bragg CDI, and nanodiffraction. And these are some examples of application. This is an example of nano XRF. So essentially, it's a mapping of a semiconductor at the nanoscale, and we can see the different elements with a sensitivity of ppms produced on these scales. So we can essentially study the composition of materials at the nanoscale with the sensitivity of ppm. And we can do spectroscopy. We can change the energy and see how it is absorbed by the material. This is an example of the sulfur edge of a specific molecule interacting with a gold nanoparticle. And we can see the spectrum changing as it interacts with the gold. And we can see this at the nanoscale. In terms of CDI, of coherent diffraction imaging techniques, what we do essentially, we collect the scattering light from the scattering X-rays from an organized sample. We put it in a special computer algorithm called tychographic algorithm that takes this scattering pattern and changes it back to the real space. And this produces a real image out from the scattering pattern. With the property, the very interesting property is that the resolution that can be achieved is much better than the size of the probe. Even if your X-ray probe has 15 nanometers, you can have resolutions of about 1 nanometer. This is an example of it. This is the transmission imaging of magnetostatic bacteria. So this is the imaging in transmission. This reflects the resolution or the size of the probe itself. So we have a blurry image. But when we do tychography, we go from resolutions of 100 nanometers down to 7 nanometers. And we can see the details inside the bacteria itself. So this is the power of this type of measurements. So as I said, we have two experimental stations. We have Tarumã and Sapoti, and I'll very quickly go through these different types of these two machines. One thing that we can see from these graphs here is that the flux that we are going to achieve at the Tarumã station or the Sapoti station is about 1,000 to 10,000 times higher than current third generation machines, third generation beam lines, which means that we can produce much faster experiments. Of course, we have to be worried about radiation damage because the doses will be much higher as well. So we have to be very fast on the measurements. So this is the Tarumã station. Essentially, the X-ray beam comes from this way. It reaches the sample, which is positioned on the center, and we have a variety of detectors surrounding it. So we have two fluorescence detectors here. We have a luminescence detector. We have a diffraction detector and a detector for scattered light here. And we have two optical microscopes for positioning of the samples. And the sample itself can be assembled in different types of pins, which are very close to what we have in electron microscopy. This is the actual beast. So this is the machine being assembled. This is the Tarumã station. This is as it is nowadays with the different detectors and the sample in the middle. These are the first commissioning images. So using the detector that we built here in Brazil called PyMega, which is a 2D and area detector, we could collect the beam size, the beam itself, and we used a standard to collect, to do tychography and to collect very high resolution images. So here the resolution is about 13 nanometers, and we are already achieved. As I said, we have to be very fast. So we have implemented a fly scan measuring mode, which means that the scan never stops. Essentially, the detectors run in free run mode. And this allows us to do, for instance, these measurements of this is a tychographic measurement of an area of 5 by 5 microns with 60 nanometer step in just 3 minutes. Or this, which is a piece of soil with different types of elements inside of the soil. And it is 100 by 100 micrometers in scale with 1 micrometer step size. And this was collected in just 18 minutes. So we can be very fast, minimizing the radiation dose deposited on the samples. Some examples of scientific commissioning, which I found interesting to show you here. This is a meteorite that I have been studying. It's called Black Beauty. It was recovered from the Sahara in 2011. It has about 2 billion years old, and it's a Martian basaltic breccia, meaning that it came from Mars. And we could analyze it at the micro scale, and we could understand the different the main minerals that could be seen, and we could see some iron oxides rich in titanium that we have a source of water on its formation, meaning that one measurement performed at the nanoscale allow us to infer the presence of liquid water on Mars 2 billion years ago. So I think this is very powerful and impacting. This is another place that we have been studying called the Kuruman Banded Iron Formation in South Africa. It has about 2.46 billion years old, and it's an alternation of iron 3 and silicon, essentially, deposited on the rock. And we can see these red and lighter patches of material. There is a long discussion if these structures have the influence of biology on its formation. So we have performed measurements of very small, of areas of 250 by 250 microns with a pixel size of 0.5 microns. And we can see that this is an iron map. So what we have here in lighter color is iron. And we can see that that we have this banded formation reproduced at the micron scale. And we can see that there are some filaments and some structure that resembles a network, which we are trying to show that that can be associated to the presence of a microbial mat on the past history of these samples, showing that there is a link of biology and the formation of the banded iron formations on the world. In terms of sample environments, we have a variety of sample environments. We have domes, we have samples that we have ships that can be taken directly to electron microscopes so that we can compare the X-ray images with electron microscope images. But we have a variety of sample environments. We can grow plants and make measurements of the roots. We can do microfluidics. We can control the atmosphere and do catalysis. We can do electrochemistry, and we can cryo-cool the materials down to 150 Kelvin to maintain the integrity of the sample. So we have a variety of sample environments to keep the sample as we need for the measurement. And I'm coming to the end. This is the Sapoti station. This is currently being built. It's very similar to the Tarumã station, but it's fully in vacuum and fully cryogenic, meaning that it works at all time at 90 Kelvin to maintain the stability necessary to achieve a beam of 30 nanometers and the spatial resolution that we want to attain here of 1 nanometer. This is our goal, to really be very similar to what can be done with electron microscopes, but with all the advantages of X-rays. Inside of the machine, we have the same types of detectors, X-ray fluorescence, X-ray absorption, diffraction, and scattering to produce images. And this is an example of an outcome of such CDI techniques, the tychography that I have been talking about. What can be done with these machines? This is an example of a work of my student, Lara Maldanis, again, her PhD. She studied these formations from these bacteria from the Gunflint Formation in Canada, which have about 2 billion years old. So these are fossilized bacteria, and we could study its structure inside the rock without having to crack it open, with resolutions of 50 nanometers in 3D. And we can see here the minerals that were deposited on the surface of the bacteria, which are iron-based minerals, iron oxides. We can see in green the preserved organic matter on the samples, and we can see in blue the voids or the empty spaces inside of it. So we can see, we can do morphometry, so we can measure the morphology of the sample. We can measure the composition, and we can measure the structure of these materials without having to open the sample at all. And we have been proposing this technique to be used on the samples being returned, that are going to be returned from Mars, in order to search for signs of life, such as this one. So we hope to have contributed a bit to this field of research. But well, we have a lot of support labs at Synchrotron. We have biology labs, cryogenic labs, cell culture labs, ultramicrotomy, electron microscopy, FIB, focused IO beam for cutting the samples, plant incubators, glow blocks, rock cutting and polishing, and sample preparation and sample environment preparation labs. So this is all available for the users when they come. The idea of Sirius is really that the user comes with the sample and the idea, and we help them to produce very good science out of it. And with this, I'd like to finish. I leave here my email if you want to ask any specific questions or make contact. But of course, we have time for questions on the Q&A. Thank you very much. Thank you, Mattia. Thank you, Jana. And I finish here.